Hello everyone. So today we will continue with optical sources. Last time we had discussed about light emitting diode. Today we are going to discuss about another type of optical source which is called as laser. So under this topic we will study about laser characteristics. We will study about how laser operates and what are the typical bandwidth of a laser diode and what is a modulation bandwidth, and we will understand different types of laser, types of noise it produces, so on and so forth. So let us start our discussion with laser. So laser, first of all, is a coherent source of light. So we need to first understand what is coherency. And the coherency can be of two types. One is temporal coherence, which is in time. The other one is spatial coherence, which is in space. So let us try to understand temporal and spatial coherence. So temporal coherence. Suppose there is a waveform, something like this. It has some amplitude A1 at time t, and at time t minus tau, it is A2. So let us define a temporal coherence function as how this A1 and A2 are correlated. Temporal coherence function can be defined as R tau is equal to minus infinity to infinity AT into A conjugate T minus tau dt. Now we will see that this coherence function, which is R tau, forms a Fourier transform pair with S omega, which is power spectral density. This we should recall from signal and system course, power spectral density. Okay, so if R tau is something like this, this is tau is equal to 0, this is R tau. That means if you correlate when tau is equal to 0, that correlate with the point itself, then it has maximum R tau, and as the tau increases, the R tau value goes down. So if you get a curve like this, then this is actually called as the coherence time. Where the value of R tau has fallen by some factor that depends on the definition, whether it is 90% or 50%. So that tells you the coherence time. And this coherence time, and if I take the bandwidth of this, the Fourier transform of this, then this is sort of Gaussian, so you will get a similar curve, Gaussian curve here. So this is F, and this is actually the bandwidth. So now let us try to understand with some limits, with extreme limits. For example, if you have the correlation function something like this, and it is 0 for rest of the time, it is maximum at tau is equal to 0. which means this waveform correlates only with itself, with the same point. Otherwise, it is zero. There is no correlation with any other point in this waveform. So, and if I take the Fourier transform of such a thing, it basically gives you a flat response. That is, this is f, and this is s omega. This was s omega. So the bandwidth is actually infinite. And which means the source is incoherent in time. Right. So now let us try to understand the coherent in. We can take the reverse of it. That is, let me explain in the next page. If I take the reverse of this, that is, I have, this is my tau, and R tau is same for all values of tau. And if I take the Fourier transform of it, this is f. So this will give me a single line, single frequency. So this is s omega. So if the coherence, the R tau, the correlation function is flat for all values of tau, and if I take the coherence, then I get a single line. So this source is actually monochromatic. And the source will be called as temporally coherent. Okay. So now let us try to understand the spatial coherence. As I explained you earlier, that the coherence is of two types, temporal coherence and spatial coherence. I have discussed the temporal coherence, and then let us discuss the spatial coherence. So if I have a waveform which is something like this, I'm seeing in spatial domain, so, and this is a plane which is plane perpendicular to direction of propagation. And this is separated by, say, lambda wavelength. This is the T. Now, if I take, if my coherence function, the coherence function in this case will be defined as R lambda is equal to AX into A conjugate X minus lambda. So let me explain in front, in this screen, in this sheet itself. So let me redraw again. This is some waveform, and this is a plane perpendicular to the direction of propagation, plane perpendicular to the direction of propagation. and the spacing between these 2 points is say lambda, and this is t. So as you see, the special coherence function is defined as r lambda ax into a star x minus lambda. This direction is x. Now if I take the coherence r lambda, plot r lambda versus x, and if it is something like this, that is, it is 0 at all value of x, and it has maximum at x is equal to 0. And if I take, and we know that the Fourier transform of special coherence function is how the power is radiated or power is spread, or what is the pattern of power in a special domain, which we can call as power radiation pattern, r lambda. So if I plot r lambda, then this will be it will be flat here. So let me call this as power radiation pattern, power radiation pattern. So this r lambda and power radiation pattern, they form a Fourier transform pair. So when the r lambda has the impulse kind of characteristic, then the power radiation pattern is actually wide. The power is emitting in all the directions, so wide emission of power. So the power which is coming from the source is emitted in all directions. So this kind of source is actually spatially incoherent. Spatially incoherent. Because in some cases we want the power to be directional, and we don't want that power should be spread in all the directions. So on the other side, if you have r lambda, which is constant over all values of x, and if I take the Fourier transform of this will give me an impulse kind of thing. So this is power radiation pattern or density, you can write. So this is in space x, and it gives you highly directional power in one particular direction. So in this case, the power is actually emitted in all area, whereas in this case, the power is emitted in a very, very narrow, or it is focused, or it is directional. So this kind of source is called as spatially coherent source. So we have understood the difference between temporal coherence and spatially coherence. So the photons which are emitted, they'll be called as coherent if and only if they have the same energy, h nu, which basically tells that it has single wavelength, same momentum vector. It tells about the power radiation direction, that the power is highly directional, and it should be same polarization. So it should follow this triplet, the energy and the momentum and the polarization. So laser devices in generally, they are coherent both in time and space, which means they are spatially as well as temporally coherent. And the benefit of spatially coherent is that the light is in one direction, so you can couple maximum light in the fiber, right? And if you have, for example, a free space link, and this is the receiver here, and you want that there should all the light should get focused on the receiver. So you're looking for a very coherent, specially coherent light, so that it is directional and falls onto the receiver. So specially coherence is the property of temporal coherence is also this is property of special coherence is used here. So this is it gives you actually the advantage in terms of distance. So if your light is directional, not spreading in all the directions, then it will give you advantage of that you can cover a long distance, and more light can be covered into the fiber. So which gives you ultimately a long distance communication. If the laser is temporally coherent, that means it is emitting almost monochromatic source, but in actual practice you don't have monochromatic source. So it is roughly, there is some bandwidth delta lambda. We'll discuss about this delta lambda a little later. But the advantage of narrow spectral with delta lambda is that in the fiber, the wavelengths which are there inside this delta lambda, when they travel inside it, so they may not be significant amount of dispersion. If this is wide, for example, because each wavelength will travel at different velocity, which will arrive at different times. So you will see spreading of pulses. Whereas if it is narrow, you have only few wavelengths and they are very close to each other and they travel almost with the same velocity. So you may not get dispersion of pulses. So you can have high data rate. So temporally coherent and spatially coherent are both useful property which can give you a long distance communication and which can give you high data rate communication. So after understanding the coherency part, now let us try to understand the basic mechanism of laser diode. So there are three processes which are happening in matter, and those processes are absorption. I'll discuss in detail about this absorption process, spontaneous process, and stimulated process. Let us understand what are these processes. So the absorption process is actually, if you consider a two-level system with energy E1 and E2, and there is some flux density, say rho nu, is falling on the matter. This is E2. Then the electron from low energy state will go up because of this rho nu. So the final state will be, this is E1, this is E2. The electron has come here. So this process is called as absorption. The second process is spontaneous. Spontaneous, what happens? Again, let us consider two energy level system, E1, E2. The electron which is there in the excited state naturally or spontaneously falls down to the low energy state, and in the process it will emit energy. So this energy and the electron has come here. So this is the final state, and this was the initial state. So this process is called as a spontaneous emission. This is a natural process happening all the time. natural process. The third process is stimulated. So what happens in stimulated? Again, let us consider two-level system, E1 and E2. And if the light flux density falls, rho nu falls onto this matter, then electron from here is actually forced to come down to lower energy state. And in the process, it is emitting more photons. So this is E2, this is E1. So this process where you're forcing the electron to come down as a result of this input flux density is called as stimulated emission. This is a forced process. You're forcing electrons to come down. Forced process. So in a two-state, which I have discussed here, the transition involving absorption, spontaneous and stimulated emission under thermal equilibrium, the total downward transition is equal to upward transition in a steady state situation. So in this case, it is upward transition. In this case, this is downward. In this case also, this is downward. So upward transition is equal to downward transition under steady state or under thermal equilibrium. Let us write some basic equations, which we will not solve those equations, but I'll just mention about those equations. So if I consider, for example, the absorption part, then the absorption rate R12 is equal to rho nu, that is a flux density falling onto it, and it is proportional to the number of electrons in the E1 level, which is say N1, and the probability is the probability that electron is here and is absorbed is given by B12. These are transition probabilities, so this is transition probability. Similarly, I can write for spontaneous emission. So spontaneous emission will be R21 because it is coming from E2 to E1. This is spontaneous. This will be it is proportional to actually a number of electrons in high energy state, that is E2, which is N2, and the transition probability is A21. So this is the transition probability of going from high energy state to lower energy state, which we call it as spontaneous emission. The third rate is stimulated. So the stimulated will be again R21 stimulated, and it will depend how many electrons you have in the high energy level, that is N2, and rho nu is your flux density, and the transition probability will be B21. So these are the three basic equations, and then to solve for different transition probabilities A21, B12, B21, we'll have to equate all the downward transition equal to the upward transition, and then using some mathematics you can find out the values of A21, B12 and B12. So now let us understand some interesting facts which are happening. So if you see the number of electron density at energy E1 is given by e raised to minus E1 by kT, where k is the Boltzmann constant and T is the temperature. Similarly for N2, it is given by e raised to power minus E2 by kT. So if I take the ratio of N1 by N2, it will give me e raised to power minus E1 plus E2 divided by kT, which is nothing but h nu. This difference is h nu here. And if you put the values of Planck's constant and some typical frequency and Boltzmann constant and temperature, you will see this value is very, very high. It is so I think of the order of 10 to the power 32. It's quite high, which actually means that at steady state or under normal conditions, all the electrons are here at the E1 level. And practically there is nothing at E2. This is what it means. E2 is empty and E1 is full. Now I try to calculate the stimulated emission rate versus spontaneous. I find out the ratio of stimulated emission rate and spontaneous emission rate. So again, this is actually given by a formula 1 by e raised to power h nu minus h nu by kT minus 1. So we have already earlier seen that e raised to power h nu kT is very, very high. So 1 divided by some big quantity gives you very, very small. So what basically it means that stimulated emission rate is actually not happening practically, right? Because this ratio is very small. So under normal conditions, there is no stimulated emission happening. So this is another interesting fact. This is one fact. The another fact is this. And now if I find out a ratio of stimulated emission rate with respect to absorption rate, this gives me e raised to power minus h nu by kT. And since this was e raised to power h nu by kT by putting typical values of h nu and k and t, this is going to be very, very small, which means the stimulated emission rate is also negligible, as in comparison to absorption rate. So earlier when we were discussing about those probabilities A12 and B12 and B21, it can also be found that B12 is equal to actually B21. Then that means the probability of stimulation and the probability of absorption actually they are equal. But this condition is not there at the moment. We have to create this condition, right? So right now, stimulated emission rate and absorption rate, this ratio is quite small. So you have to create a condition, and we understood from earlier analysis that B12 is equal to B21. That is the transition probability of stimulated and absorption. They are same, but it is not happening naturally. So if you want that stimulated emission should dominate, then you have to create that condition. And how do you create that condition? You pump some of the electrons from here to the higher state. And in fact, you suppose this is n number of electrons roughly, and you should pump greater than n by 2. Then the stimulated emission will dominate. Stimulated emission will dominate. So what actually I have done essentially by lifting the electrons from the ground state to the higher state, more than half, I have done population inversion. So the moment I achieve this population inversion, the stimulated process takes over, stimulated process dominates, and we get stimulated emission. This is the basic principle of laser. So you have to create, you have to pump, you have to give energy using a pump and transfer more than half of the electrons from the ground state to the higher state. And then when flux density falls onto the matter, it forces those electrons to come down and they all emit photons. And this process is called as stimulated emission, and the laser is based on this process. So basically there are different types of laser system. We'll discuss the 3-level system first. So 3-level system is basically you have 3 levels here. So this is energy E0, E1, E2. So first you give some pump energy. It can be a source, another source of light, so that the electrons are lifted and they are lifted to energy level E2. In E2, they stay here for very, very less time, and then there is a fast decay, a rapid decay. To E1, and from E1 the electrons, they fall onto the ground state and they emit energy. So this is an example of a typical 3-level system, and this is actually pump energy, and this is corresponding to this frequency or this wavelength. So typical pump energy which is used is in 980 nanometers or 1480 nanometers. There are different wavelengths which are possible. That depends on the material which you are using. So by using pump energy, you are shifting the electrons from the ground state to high energy state, and they stay there for very small time. So there is a rapid decay to the lower energy state, that is E1, and from E1 to E0 there is a emission of light, and this is your input signal, rho nu. So it will force all those electrons which are there in the E1 state to fall down to E0 and then emit more number of photons. So this is basically a 3-level system. One can also use 4-level system. Here in this case, you have to practically pull at least half of the electrons to the higher state. So you require more amount of pump power or pump energy. But if you have a 4-level system, this criteria of high pump energy is relaxed. So let us understand this. So suppose there are 4-level systems starting E0, E1, E2, E3. So this is your pump energy. And then there is a fast decay, rapid decay here. So even if one electron has come here in this point, at this point, there is already population inversion with respect to E1. There is already a population inversion, right? So you require less amount of pump energy to create population inversion. And the moment this is the lasing part, the electron will fall to E1 and emit light. So this is lasing operation here. So I forgot to write here as lasing. So, and then from E1 again there is a rapid decay. So this is an example of a 4-level system. The advantage of 4-level system is that you require less pump energy to create population inversion, which is a requirement for lasing. So let us after understanding this 3-level system, 4-level system, let us now try to understand the temporal coherency part, which we had discussed. Why a laser source is a temporal coherent. So now once you have achieved a stimulated emission, I can always ignore spontaneous emission, because now stimulated emission is dominating. So spontaneous emission is much less as compared to stimulated. So I can simplify my analysis by ignoring spontaneous emission. So the net downward transmission rate will be that is rate of NP, number of photons generated with respect to time, is minus this. So one of them is stimulated, the other is absorption, and we are ignoring or neglecting the spontaneous emission. So this is the rate. And as explained you earlier, that if you are solving those Einstein relations which I had given you in the beginning, then basically this B12 is equal to B21. That means the probability, the transition probability of absorption and transition probability of stimulated, they are actually same. So this B12 can be taken common. So this becomes N2 minus N1 rho nu. And if I multiply by h nu NP, then I get this equation. This actually comes from the fact when you also consider black body radiation theory, because this matter is emitting some light. So this can be equated to a black body radiation. And if you equate these Einstein relationship with black body relations, then you get the value of B21, which is written here. This will be C cube divided by 8 so the value of B21 or B12 will be C cube h nu over 8 pi nu cube n cube tau 12, where c is the velocity of light, h is Planck's constant, and nu is the frequency, n is the refractive index of the material, and tau 1 is the average spontaneous time, lifetime, average spontaneous lifetime of the photon. So this becomes rate of flux density, that is d rho nu, because Np into h nu is flux density rho nu. D rho nu divided by dt is equal to this. And since the photon which is generated inside a material is moving in all the directions, so this can be written as in the form of dx, where x, the distance traveled, is c by n and is refractive index into time. So if I differentiate dx by dt, I get c by n. So this becomes, actually this dt will not be there. Okay. And so you can write this equation as d rho nu by dx is equal to c square h 8 pi nu square n square tau 1 2 n2 minus n1 into flux density. So this whole thing can be written as, say, G, which is actually called as the gain. And if I solve this equation, so this will become flux density as a function of distance inside the cavity, laser cavity, and a function of frequency. So this is given by some constant rho f at x is equal to 0 into e raised to the power gx. So notice here that g, the gain factor, is writing on the exponential. So the power as a function of x is proportional to e raised to the power gx. It is growing very rapidly because this g function is coming in the exponential. And if you see this g function, the g is actually c square h over 8 pi nu square and square tau 1 2. That means the gain is actually proportional to, inversely proportional to nu square, also inversely proportional to n square refractive index, and is also inversely proportional to the average spontaneous lifetime of the photon. Which means, actually what it means that if tau 1 2 is small, g is high. Which means if you consider two level system, and if this tau 1 2 is very, very small, that means it is spontaneously falling to ground state very rapidly, and this is aided by the input flux density. So that is why this gain is actually, the spontaneous is actually adding to the gain. So it explains why g is proportional to tau 1 2. So this is how the flux density will grow inside the cavity, which is e raised to power gx. So now let us try to understand, g, this particular g, this g. Sorry, I did not write the other things, n2 minus n1 also, right? Sorry. So this g is this, and g is proportional to n2 minus n1. So this g will be negative if n2 is less than n1. That means the number of electrons in n2 is less than at n1, that is at energy E2 as compared to E1. So that means there is no gain here, no gain. If g is 0, which means number of electrons in the E1 state and the E2 state on an average they're same, so the gain is unity. So it's a transparency condition. Neither gain nor loss. Transparency condition. If g is positive, that means n2 is greater than 1. This is a condition of population inversion. You have more number of electrons at higher energy, that is at E2. So this is a condition for population inversion. So g is positive if n2 is greater than n1, and it's a condition of population inversion. If you recall last time when we were discussing about light emitting diode, the gain or the power which was getting generated from a LED was proportional to n2 minus n1. And it gave me something like this, though this was EPH and this was 2 kT, and it had a peak at band gap energy plus kT, and this Eg was 0 here. This is Eg. Whereas in case of laser diode, if I plot the same curve, EPH, and because the G is riding on the exponential and the power is increasing at exponential rate, so the same curve will become very narrow. And this, in this case, this is the spectral width of the laser diode because of this the whole stimulated emission process. So this is the spectral width. So the spectral width of a laser diode is very, very low, and typical laser diode has a spectral width of 0.1 nanometer to few nanometers. Whereas in the LED case, we had discussed or we had calculated the order of 70 to 100 nanometer. So we can now say that this source is temporally coherent. So we have done some analysis and understood why the spectral width in case of laser diode is very less and the source is temporally coherent. Now let us see the other part, that is a spatial coherence. So inside a laser cavity, for example, the electron is moving with some propagation constant beta, and it is actually going in all the directions. Whereas we want some useful light to come out through one of the facet of this structure. So in order to do that, two mirrors are kept at the ends, and the electron, which is for example generated here, has some propagation constant beta, strikes this mirror, gets reflected, strikes this mirror, gets reflected, comes back here, and in the process some of the energy comes out, because the reflectivity of the mirror is such, say this is R1, this is R2, that some percentage of the light comes out, the other stays inside the laser cavity. So in order to have spatial coherence, we want to have high gain, that is more and more stimulated emission, so that it compensates for the loss. And the loss is happening because of some light is coming out of this R1 or R2, and some absorption happening inside the material, some scattering happening inside the material. So we want to have some sustained oscillation and want to have continuous output. So I need to ensure that laser acts as a oscillator, not as an amplifier. So in order for laser to have sustained oscillations, we want to use this laser as an oscillator, and for that we need to have some few conditions to be satisfied that we will understand. So first let us understand what is the electric field in the z-axis. This is given by EZT, IZ. This is optical field intensity, optical field intensity into e raised power j omega t minus beta z. If the electric field is in the z-axis, and this IZ0 is given by e raised power tau g minus alpha z, where tau g is the gain, and this is the confinement factor, how the light is confinement factor. And this basically gives you some idea about the gain, the total gain in the system. And then there is some loss happening, which is alpha, and this loss is some light coming out of the mirror, some light is getting absorbed, some light is getting scattered. So this is actually the net gain. So Iz as a function is a function of because earlier just now we had seen in the last lecture that the growth of flux density is e to power gx. This is how the flux density is growing, where g is the gain. So in our case, the net gain is tau g minus alpha, which is here, and x, this was in x, and this is in z direction. So this is how the optical field intensity is growing. Iz is equal to I naught into e gamma g minus alpha z. And if you see, this distance is L. If it travels a distance of 2L, which means suppose a photon is generated here, it travels this distance, gets reflected from the mirror, comes here, again reflected from the mirror, comes back to the same position. So basically, it has traveled a distance of 2L, which is here. So this I2L will be I0 into the total distance. This is 2L, and this is the net gain, and these are the reflectivity of the two mirrors, because it has encountered two reflections, one at this point and another at this point. So this is the optical field intensity after traversing a distance of 2L is equal to I naught, the initial, which is when it was generated in the middle, and R1, R2, reflectivity of the mirror, into e raised to power g, which is the net gain, into 2L. So for laser to act as an oscillator, we need to satisfy two conditions. One is the loop gain must be unity, that is I2L is equal to I0. The intensity when it has traversed a distance of 2L should be equal to I0. So this is one condition. The other condition is a phase condition, which happens typically in an oscillator. So e raised to minus j 2L, this is a distance, into the propagation constant should be 1. So these two conditions should be satisfied. It will ensure that the laser operates in a continuous fashion, or it is in an oscillatory mode. So if I use one other condition, that is I2L is equal to I0, and put in this equation here, I get R1 into R2 e raised to power gamma GTH. This is the threshold gain, because this is the gain which I require for oscillation. So this G becomes GTH, G threshold, minus the loss into 2L is equal to 1. And I now, without losing any loss of generality, I can assume this gamma to be 1. So this is slightly, becomes little easier and modified. R1 into R2 e raised to power GTH minus alpha into 2L is equal to 1. So this is one other condition. So this is rewritten here, and I can find out the value of GTH by taking log natural both sides. So this gives me GTH minus alpha into 2L is equal to log natural 1 by R1 R2. And this is the expression for the G threshold, that is the gain required, which is alpha, the loss happening inside the cavity, laser cavity, plus 1 by 2L into log natural 1 by R1 and R2. So let us try to find out some typical value of GTH. So suppose I have a laser cavity and the length is say 200 micrometers, and the average loss, that is alpha, is given by 1000 meter inverse. This is per unit distance. So, and the material of this laser cavity is gallium arsenide. The refractive index is about 3.6. Then we need to find out what is the GTH required for sustained oscillation. So if you put in these values in this expression here, you get GTH as, recall that R1 and R2 can be calculated as N1 minus N2 over n1 plus n2 whole square. This is how you find out the reflection coefficient. So this is n1, this is n2, then this is interference, right? So by putting some typical values of R1 and R2, I get GTH as 6697.17 meter inverse or per unit meter. So this is the value for the GTH. Now let us try to understand the phase condition. We have understood about the gain part, and now let us try to understand the phase condition. So as I explained that the phase is for a distance of 2L. So whenever, suppose this photon is generated, it gets reflected from here, it gets reflected from R1 and then travels and then again reflected and comes back to this. The total distance covered is 2L. So the phase condition is that e raised to minus j 2L into beta should be equal to 1. So this can be written in this form. This 1 is equal to e raised to minus j2 pi m. So this gives you 2 beta L is equal to 2 pi m, where m is some integer. And if you see m is equal to beta L by pi, so I get this value of beta L by pi. So this condition will not be satisfied for all the frequencies. So this will be only, then I can write this actually little more in new form and in the frequency form. So beta L is actually 2 pi n by lambda, that is beta, into L by pi. And if you simplify, what you get is 2nL divided by C into I, where n is the cavity length and n is the refractive index and nu is the frequency. And this is m. So this m can take some value, m is equal to 1, 2 and so on and so forth. That means this condition will be satisfied only by some few frequencies, which are say nu1, nu2, nu3. It is not satisfied by all the frequencies. So what happens actually in an actual laser diode, you get different frequencies here. They may change in amplitude, but you get different frequencies which are governed by these equations. And if you take envelope of this, so this is something like this, right? So this kind of laser where many such M are excited, and the dimensions are such that many modes are excited, such kind of laser is called as MLM lasers or multi-longitudinal mode lasers. So suppose I want only, and this will have some bandwidth or some spectral bandwidth, width. So suppose ideally I want, a single, wavelength or to be excited. That means I should have m is equal to 1. Only in that case I will be able to get only one mode. So if I take m is equal to 1, then and put the value of 1 here, then I get some L as lambda by 2n. And if you put some value of lambda, say 1550 nanometer, and n you assume to be 3.6, so this L is actually very, very small. I mean, one can construct a laser, but this L is going to be very small. When this L is very small, it cannot, such kind of source cannot emit high power. Otherwise, it will get burned because, the power generated per unit area will be very high. So, if you want to have a single mode laser, then one has to keep the laser cavity length very, very small, and which you may not get good enough power if your L is very small. So now let us try to find out the separation between two modes. So as I told you, there is SLM. If it has only one mode, that is called a single longitudinal mode. The other one, which I had explained, is multi-longitudinal mode, where you have, many modes. And single mode will have something like this. So now if I want to find out what is the spacing between these two modes, and once I know this is spacing and number of modes, so then I can find out the spectral width. So number of modes and spacing, if I know these two factors, then I can find out what is the delta lambda, or the spectral width of the laser diode. So to try to find out the separation between two modes, m is equal to 2nl divided by c nu m, corresponding to mth mode. This is what we did just now. And if you want to see m minus 1 mode, this is say m mode, this is m minus 1, this one. This will give us 2nl divided by c nu m minus 1. And if I find out the difference between nu m minus nu m minus 1, it will be something like the c by 2nl. And I can write this in terms of delta lambda by using expression delta lambda is equal to delta nu over nu. So this is in delta nu, and I want in terms of delta lambda, because normally the spectral width is expressed in terms of delta lambda or in terms of nanometer. So this will be delta lambda square divided by 2nl. So if I take a simple example and to give you some idea about delta lambda, so suppose I have a Fabry-Paro injection laser diode with a cavity length of 500 micrometers, and lambda is equal to 850 nanometer. I mean, this is the lambda I'm trying to work at. Lambda is equal to 850 nanometer. So I need to calculate what is the wavelength separation given the refractive index of the material is 3.6. So a simple calculation will give you delta lambda as 0.2 nm. And suppose 10 modes are supported by the diode, that means m is equal to 1 to 10, then the total spectral width will be actually roughly 0.2 into 10 or 2 nanometers. So this explains about the spectral width, and now let us try to find out what is the trade-off while designing a laser diode. So there are three things which is in the hands of designer: the length of the cavity and GTH and M. So as you see, there's a trade-off between L, GTH and M. So if you increase L, suppose the L increases, then if L increases, GTH will increase, GTH will decrease. And if L increases, in this expression if you see, the M is increasing. That means the number of modes which are supported are increasing, which actually effectively is increasing your spectral width, right? And when L increases, you have larger cavity, so more power can be generated, right? But then at the cost of M is also increasing. So the number of modes are increasing. Effectively, the spectral width is increasing, and GTH. So if you see, there is a interplay between these three quantities. That is the cavity and the threshold required for population inversion and the number of modes. So there's a trade-off between these three quantities. Now let us try to understand how do we bias a laser. So if you see the characteristic of a LED, for example, that is, if I change the current here and the power here, it is almost linear. Whereas in case of laser diode, when I am changing the current and this is the power, so initially, population inversion has not happened. So spontaneous emission may be happening in the divider. It may be acting for some time when there is a small amount of current. There will be very little power, which is actually, this is a spontaneous region, spontaneous. The population inversion has not occurred till this point, spontaneous emission. As soon as you are able to achieve the population inversion, the stimulated emission kicks in. And as soon as the stimulated emission kicks in, there is a sharp increase in power. So there is some threshold, ITH. After that, there is a sharp increase in power. So this is a typical characteristic of a laser diode. So it's a threshold device. After a certain threshold, there is an increase in the power, whereas in the case of LED, it was almost linear. So now when you are using this laser diode, where should I bias my laser? Whether I should bias my laser at this point, say I call it point A, or I call this point somewhere here as point B. So if I bias at point A, so there are two issues. In order to go from non-lasing condition to lasing condition, it will require some time. Some finite time is required, some finite time. Which will actually limit your data rate, the rate at which you can modulate your laser diode. So this is an issue if you bias at point A. Although you get good extinction ratio is in the sense power when there is no emission or at say 0 and power at 1, because when you are modulating your laser diode, suppose this is your laser diode and you are modulating with some 1 0 1 0. So whenever there is a 1, it is emitting this amount of power or whatever maximum power, and whenever it is 0, it is emitting this power. It is emitting this power which is there corresponding to point A. So the extinction ratio is defined as power at 1 level divided by power at 0 level. So extinction ratio is good here because the power at 0 level is almost 0. And power at 1 level is quite high. So that ratio is very high, or extinction ratio is very high. So at the receiver, when you're decoding, it becomes a little easier because the difference between two power levels is quite high. So you are able to find out the difference between logical 0 and logical 1. But the issue is that, going from 0 to 1, it takes some finite time, so which may affect your speed with which you are modeling your laser diode. Suppose I bias at point B, bias at B. Your extinction ratio has gone down because, the power at this point and this point, you require very less amount of I to go to 1 power. So you have to be really very operate in a very controlled environment. And moreover, when you are biasing at B, always some current is flowing in the device. So always some current, because you are biased at B, so always there is some current flowing in the device. So there are two issues, but the time to go from 0 to 1 is very, very less. So there is a compromise that the extinction ratio might be little low and always some current is flowing. But as far as modulation bandwidth of the divide is concerned, you are able to achieve much higher value as compared to if you bias your laser diode at point A. So ideally in practice, you bias the laser near the knee point because your main concern is to modulate the laser at high speed. So you modulate near the knee region, which is close to B. So this is how you bias your laser. And also the characteristic which I have drawn here is function of temperature. So as temperature increases, for example, this is T1, this is middle one is T2, T3, and this is increasing order. So with increasing order, your threshold also changes, threshold value, and the characteristic also changes. So in order that you get constant output power from the device, you have to use some mechanism so that you control the junction temperature of the laser diode, and you don't if it is not controlled, then the output power will change because, see, these are different powers you're getting at different temperatures. So for maintaining the same, so there are some techniques which makes the junction temperature constant. So one of them is use of thermoelectric cooler. So it basically senses the temperature and accordingly pushes more current or less current depending upon the temperature, and the power output is held constant. So this is highly temperature dependent. So some mechanism should be there to arrest this variation in power with respect to temperature. Now let us understand about the modulation of laser diode. So the modulation of the laser diode is given by defined as follows. So 1 by TH, where top EH is the average lifetime of the photon, either it comes out of the device or it gets absorbed. So you find out the average lifetime. So the top pH is called as the average lifetime of the photon before it comes out or gets absorbed inside the material. So that 1 by T pH is, top pH is given by C by N into gain. And gain we have seen for the lasing condition was G was equal to alpha plus 1 by 2L log natural R1 over R2. So for N is equal to 3.6 for gallium arsenide, suppose I take cavity length as 250 nanometer, takes typical reflectivity as 0.32, and the attenuation or the loss part is 1000 meter per inverse, and plug in these values will give me top pH as 2.1 picosecond. And if I take just the frequency response or the inverse of this, it gives me typically 8 gigahertz. I can modulate the laser diode at this speed. I mean, this is as far as direct modulation is concerned. If you want to have further high this thing, there are other techniques using indirect modulation. But typically, you can modulate laser diode at very high frequency of the order of 8 gigahertz. This was not the case for LED. LED, you were able to modulate only few tens of megabits per second, whereas for laser, it is in terms of gigahertz. So now let us try to understand the external quantum efficiency of laser diode. So the internal quantum efficiency is actually defined by number of photons created in the laser cavity how many photons are created in the laser cavity, and divided by the number of injected carriers. So this gives me an internal, and neta internal, this is of the order of 0.6 to 0.8. And the neta external, that is external quantum efficiency, is neta internal into the net gain. This is the net gain because this is the gain part, or this is the loss part, and divided by the gain part. This gives me external quantum efficiency, and I know the expression of GTH, which we have done earlier. And using that expression of GTH, we can find out this ratio, and after doing some calculations, what you get is neta external into internal frequency, which is of the order of 0.6 to 0.8, 1 by 1 plus 2 alpha L log natural 1 by R1 R2. So this is the typical external quantum efficiency of a laser diode. Now let us understand briefly about some types of laser which are frequently used in communication, and also during the course optical wireless communication we will see similar kind of lasers are used for optical wireless communication also. So one of the common type is DFB, or distributed feedback. Feedback laser. So what happens in distributed feedback laser? You have this is your laser cavity, and this is your say N type. This is your active region. And this is a P-type material. And you construct some sort of grating here. And the property of this grating is that depending upon the spacing or the period of this grating, some particular wavelength of the light is reflected back and others are transmitted. So basically what I am doing here, I am making this as a wavelength selective device. Wavelength selective device. So what is happening here? So, this is my grating, and say this period is capital lambda. So, and this direction is beta, propagation constant, and this direction is minus beta. So if the reflected light if it meets this condition, there is beta propagation and the reflected part will be minus beta. If this is equal to 2 pi over lambda, then there is a strong coupling of the light. So the light only which is defined by this expression, only that particular wavelength will be reflected back. The rest of the part is reflected in the other direction, which means I have achieved some sort of filtering, or I have made the device as wavelength selective, only one particular wavelength. So I'm trying to make the laser spectral width very, very narrow. I mean, initially it has wide bandwidth. I mean, it had multi modes, but I want to make it a single mode kind of laser. So for making the single mode, I'll be using this some grating structure which is embedded in the device. And then if this condition is satisfied, which is called as Bragg condition, that particular wavelength, which is defined by this that is 2 beta is equal to 2 pi by, this is the period of the grating, and beta is becomes pi by lambda. So that corresponding to this beta, that particular frequency or particular wavelength is reflected back. So such kind of lasers are called as distributed feedback. So the feedback is distributed throughout the region. So such kind of lasers will have very, very narrow spectral width of the order of 0.1 nanometer. Of course, the power will go down, but then you get very, very narrow spectral width lasers. So these are the commonly used lasers for high data rate applications, whether it is free space optical wireless communication or optical communication using optical fiber. The laser also has some sort of noise. So those photons which are generated either through stimulated or through some spontaneous process, sometimes their phase is different. So it results in some sort of noise, both in frequency and phase. So this is referred as laser noise. And also, as I explained you, the laser structure has some mirror. So some of the light goes out and some is reflected back into the materials. If it is coupled, through some fiber or somewhere, then the light might get reflected back. So this will generate some sort of noise, which is called as reflection noise. So this is another type of noise which is produced in the laser. And the third one is mode partition noise. Mode partition noise is, as I explained you earlier, the laser emits, for a multimode MLM laser, multimode longitudinal mode lasers, there are many modes. Suppose this is at time t1. At t2, the power in these modes may change. So it will become something like this or something like this, something like this. This is at t2. But if you take the average at different times, you get almost a steady power as far as envelope is concerned. But within the device, this power is continuously changing for all these modes. So because of this, some sort of noise is generated into the laser diode, which is called as the mode partition noise. And the third one is aging effect, because you have some mirrors here. The life of the mirror, with constant reflection and constant continuous operation, this reflectivity is affected. It may go down. So this results in some sort of reduction in the power output. So this is another point one should consider, the aging effect of the laser. So these are some of the impairments which happen in case of laser. So finally, if I compare the difference between LED and laser diode, it is listed here. So if you see the output power in LED is of the order of, typical is microwatts, whereas laser diode can give you high power. Right? I'm talking about a semiconductor laser, but there are other lasers, gas lasers and all that, they emit very, very high power. But typical semiconductor laser can give you few tens or few hundreds of milliwatt. The spectral width is very high in LED, which will restrict your transmission rate. Whereas in laser diode, for DFB, for example, is 0.01 nanometer, but without DFB or normal lasers will give you some few nanometers, but still very low. So you can get a longer distance communication using laser diode. Because the spectral width is low, the dispersion will be low. The modulation bandwidth is few megahertz, whereas for laser diode, we also saw is about few gigahertz. Electrical to optical conversion in case of LED is very low, 10%, 20%. Laser diode is about 30 to 70%. As far as eye safety is concerned, it is eye safe because power output is not very high, and laser diode should be made eye safe because if the power is high, then it might damage the eye. So depending upon what is the exposure time and what is the wavelength and what is the power, there are some eye safety levels are defined. So the laser power, if you are operating in an environment where human beings are there, has to be controlled, and it has to be within those safety limits. So it must be rendered eye safe. The directivity of the beam is broader and spreading because it's a Lambertian source. We discussed in discussion when we were discussing LED that beam is broader and is spreading, whereas the laser diode is spatially coherent, and that is why the beam is directional and is highly collimated. The reliability of LED is very high. Laser is moderate because there are some mirror element, so which make the reliability a little low as compared to LED. But even then, the reliability of a typical laser diode is quite high. The coherence, LED is a non-coherent source. We had a good discussion about the coherency part, and the laser diode is coherent. We discussed both the temporal coherence and the spatial coherence. Temperature dependence, there is no temperature dependence in case of LED, whereas the laser diode is highly temperature dependent. The output power is highly temperature dependent, and you should have some mechanism to control the temperature if you want to keep the power output constant. The drive and control for LED is very, very simple. Whereas for laser diode, you have to keep the threshold constant, you have to keep the temperature constant. So there is additional control circuitry required to make threshold and temperature compensation. So it's a little complex as compared to LED. Harmonic distortion in LED is high, where laser diode, because it is essentially a single source of light ideally, so it is quite less. Receiver filter is wide because the light is getting emitted from in a wide direction. So the receiver which you use, actually, if you want to collect the whole light, it should be wide angle. So it will collect more noise as well. So the noise floor actually increases when you're using LED and receiver as a pair for communication. Whereas laser diode is highly directional. The receiver which you are going to have is also very, very narrow. So the noise collected is also less. So basically the noise floor gets reduced when you are using laser diode. And the cost, of course, is LED is low and laser is somewhere moderate to high. So we have, this concludes our discussion about the sources. So we have discussed both LED and laser diode, and we understood about the spectral width of LED and laser diode. We also understood about the incoherency and coherency of these devices. We also understood what is the typical modulation bandwidth of LED and laser diode. So this source is normally used in optical fiber communication, as well as we will see the LED, which are actually used for illumination, will be used for communication as well. So we are going to have extensive use of LED for communication along with illumination, and the laser diode will be used when we discuss about the outdoor optical wireless communication from point to point, like free space optics links, where generally laser diodes are used. So we will see the application of these devices in future classes. So here we will end the discussion on optical sources. Next, we will take up discussion on the photodiode. What kind of different photodiodes, their frequency response, that we are going to study in the next class. Thank you.